Today we shall study about dual nature of radiation and matter in modern physics. British physicist J.J. Thomson was the first by applying mutually perpendicular electric and magnetic fields across the discharge tube to determine experimentally the speed and a specific charge to mass ratio E by m of the cathode ray particles. They were found to travel with a speed ranging from about 0.1 to 0.2 times the speed of light, 3 × 10 to the power 8 meter per second. The presently accepted value of E by m is 1.76 × 10 to the power 11 coulomb per kg. Further, the value of E by m was found to be independent of the nature of material or metal used as a cathode or emitter or the gas introduced in the discharge tube. He named these particles as electrons and suggested that they were fundamental ultraviolet constituent of matter. He found that the charge on a wild droplet was always an integral multiple of an elementary charge, 1.602 × 10 to the power minus 19 coulomb. Millikan's experiment established that the electric charge is quantized from the values of charge E and a specific charge E by m. The mass of the electron could be determined electron emission. A certain minimum amount of energy is required to be given to an electron to pull it out from the surface of the metal. This minimum energy required by an electron to escape from the metal surface is called the work function of the metal. It is generally denoted by phi naught and measured in electron volt. 1 electron volt is the energy gained by an electron when it has been accelerated by a potential difference of 1 volt, so that 1 electron volt or 1.602 × 10 to the power minus 19 joule. This unit of energy is commonly used in atomic and nuclear physics. The work function phi naught depends on the properties of the metal and the nature of its surface. The values of work function of some metals are given in table 1. These values are approximate as they are very sensitive to surface impurities. From table we observe that the work function of the platinum is the highest, phi naught = 5.65 electron volt, while it is the lowest, phi naught = 2.14 electron volt for cesium. The minimum energy required for the electrons emission from the metal surface can be supplied to the free electrons by any one of the following physical processes: thermionic emission. By suitably heating, sufficient thermal energy can be imparted to the free electrons to enable them to come out of the metal field emission. By applying a very strong electric field of the order of 10 to the power 8 volt per meter to a metal, electrons can be pulled out the metals as in a spark plug. Photoelectric emission. When light of suitable frequency illuminates a metal surface, electrons are emitted from the metal surface. These light generated electrons are called photoelectrons. Photoelectric effect. Hertz. Observations. Hertz observed that the high voltage sparks across the detector loop were enhanced when the emitter plate was illuminated by ultraviolet light from an arc lamp. Light shining on the metal surface somehow facilitated the escape of free charge force particles which we now know as electrons. When light falls on a metal surface, some electrons near the surface absorb enough energy from the incident radiation to overcome the attraction of the positive ions in the material of the surface. After gaining sufficient energy from the incident light, the electrons escape from the surface of the metal into the surrounding space. Hallwich and Leonard observations. Wilhelm Hallwich and Philip Leonard investigated the phenomenon of photoelectric emission in detail during 1886 to 1902. Leonard observed that when ultraviolet radiations were allowed to fall on the meter plate of an evacuated glass tube enclosing two electrodes, metal plates, current flows. In the circuit in figure 1, as soon as the ultraviolet radiations were stopped, the current flow also stopped. These observations indicate that when ultraviolet radiations fall on the meter plate C, electrons are ejected from it which are attracted towards the positive collector plate A by the electric field. The electrons flow through the evacuated glass tube, resulting in the current flow. Thus, light falling on the surface of the meter causes current in the external circuit. So, both studied how this photocurrent varied with collector plate potential and with frequency and intensity of incident light. He undertook the study further and connected to a negatively charged zinc plate to an electroscope. He observed that the cyan plate lost its charge when it was illuminated by ultraviolet light. Further, the uncharged zinc plate became positively charged when it was irradiated by ultraviolet light. Both observed that when ultraviolet light fell on the emitter plate, no electrons were emitted at all when the frequency of the incident light was smaller than a certain minimum value called the threshold frequency. The minimum frequency depends on the nature of the material of the emitter plate. It was found that certain metals like zinc, cadmium, magnesium, etc. responded only to ultraviolet light having short wavelength. To cause electron emission from the surface, however, some alkali metals such as lithium, sodium, potassium, cesium, and rubidium were sensitive even to visible lights. All the photosensitive substances emit electrons when they are illuminated by light. After the discovery of electrons, these electrons are termed as photoelectrons. The phenomenon is called photoelectric effect. We can use the experimental arrangement of figure 1 to study the variation of photocurrent with A, the intensity of radiation, frequency of incident radiation, C, the potential difference between the plates A and C, D, the nature of the material plate C. Light of different frequencies can be used by putting appropriate colored filter or colored glass in the path of light falling on the meter C. The intensity of light is varied by changing the distance of the light source from the emitter. Effect of intensity of light on photocurrent. The collector A is maintained at a positive potential with respect to emitter C, so that the electrons ejected from C are attracted towards collector A. Keeping the frequency of the incident radiation and the accelerating potential fixed, the intensity of light is varied and the resulting electric current is measured each time. It is found that the procurement increases linearly intensity of incident light as shown graphically in figure 1. The photocurrent is directly proportional to the number of photoelectrons emitted per second. This implies that the number of photoelectrons emitted per second is directly proportional to the intensity of incident radiations.